Hello everyone. In this video I would like to talk about how the rotating calipers algorithm works. So as you know, the rotating calipers algorithm is used mainly for finding the farthest point on a convex polygon. um, and in order to understand how this algorithm works, we have to touch on some um, basic ideas and understand the basics first. So we'll go in steps. First, we'll try to understand how we should approach this problem. So let's consider a polygon like this, for example. Now, this polygon, as you can see, this is a convex polygon, and the farthest points are simple to see, easy to see, are A and B. Now, in order to understand how we can find these two vertices and to derive a general algorithm to solve this problem, we should first recall some basic facts. One of the facts is that the farthest points of a convex polygon P are 2 points or 2 vertices on that convex hull. So if you want to find out which points inside of this polygon are the farthest, then these tend to be the vertices of the polygon. So it cannot be any point inside of the polygon or in midpoint of an edge. It has to be one of the vertices. It has to be one of these guys here. So that's first fact. It can be proved. The second fact is that extremal vertices in a certain direction are also the vertices on a convex hull. So if you want to, for example, find any point in the polygon that is extremal, that is a maximal in a certain given direction, then it is also a point on the polygon. So what do we have? First, we said that the farthest points tend to be on the convex hull, and second, the extremal vertices tend to be on a certain line. So combining these two ideas, we can immediately see that A is the extremal vertex of P along the direction BA, along the vector BA. And that is obvious in this drawing. And similarly, if I take this direction from B to A, this is the VA vector. And similarly, B is the extreme vertex of P along the direction vector AB. So here we can immediately see if we are searching for an extreme vertex along the direction D, then we have to look for the opposite of D as well in order to locate the farthest points. Now the question is, so this was the first step. So essentially what we're looking is not just, so we can essentially reduce the problem of finding the direction such that the extreme vertices along that direction and its opposite vector are extremal or maximal. Or we can take a direction vector D and then find the maximal and minimal vertices. That is the extremal vertex in the direction D and an extremal vertex along the direction minus D. And then if we can select D such that the distance between those two extremal vertices is maximal, then means that we have found such a direction. So our job then boils down to finding such a direction. Okay. Now, how can we proceed from this point on? So, since we have reduced the problem of finding a certain direction, of such a spatial direction, let's look at all the possible directions for our problem. Well, we can essentially see that the set of directions in 2D tend to be, well, this is not a good drawing, sorry for that. It should look like a circle, yeah, tend to be all of the directions such that the vector from the origin to any point on the unit circle uh, is a direction vector, right? This we can call the direction space. But for reasons that will be obvious later on, we call this the normal space. Okay, so here's our set of directions D. Now, the problem here is that the set of all directions is infinite. Any direction D such that D is which is dependent on theta, which varies between 0 and 2 pi, could result in a valid direction. So apparently we cannot select and we cannot really construct a very useful algorithm if we tried all of the possible directions. So we need to be able to reduce this infinite set to a finite set. A finite and preferably a finite discrete set. So what do we have to do? In order to do this, we consider the following picture. Just, take part of certain convex polygon and zoom into that. Let's call this V1, vertex 1, vertex 2, vertex 3. This is edge 1, edge 2, etc. And here now, I will also put normals for these edges. Now, and I'm putting the normals such that the normals index and the edges index are the same as a convenience. And also for the convenience, I'm choosing the normal vectors to point outwards. Now this is a convention in geometric graphics. It will also turn out to be a useful convention for understanding the algorithm, because these normal directions will be the same as direction vectors, which we are looking for. If you want to be mathematically correct, you should be taking the normal directions to be pointing inside of the polygon, because, as you know, a convex polygon can be described as an intersection of finite number of half spaces, or a set of half spaces, and the positive sides of those half spaces defines the inside of the polygon. So convex polygon, but in this example we are taking them to be pointing outwards. So if I take this example, sadece dediğimiz gibi bir sürü şey aslında test ediyoruz böyle, demek ki şuna dikkat etmemiz gerekiyor. Şey de çok kötü ya. Bu sefer de orası değiyor. So what we have to do is we first look along direction n1. Let's say, for example, if we choose D to be the normal vector, okay, just, yeah, then we can see that the external vertices of the polygon are V1, and v2. If we choose as the n2 vector, then we see that the extremal vertices are v2 and v3. Well, actually, it's not just these two vectors. Essentially, this whole edge, if we choose the n1 vector as the direction vector, then this whole edge turns out to be an extremal geometric object on this direction. But since any point on this edge can be expressed as a linear, positive linear combination of these two vertices, yeah, such that there's always one, we can take either of the points. Okay, we can either select v1 or we can select v2. Both are fine. In fact, during the algorithms construction, we have to take consider them both. But here's the interesting fact. If we, for example, carry these normal vectors to this vertex and then consider any direction vector other than n1 or n2 such that D is a positive linear combination, strictly positive linear combination of n1 and n2, then we can see that for such a vector, the extremal vertex will be on the v2. What does this mean? This means that for certain directions, for certain continuous set of directions, the extremal vertex won't change. It will only change if we change discretely from n1 to strictly to n2. But any vector in between, if we, for example, take a linear combination, positive linear combination of n1 and 2, then the extremal vertex will be just v2 itself. So what does this mean? This means that we can restrict our set of vertices to be, set of search directions to be n1, n2, all the way through nm. So what does this mean? So this is an important step because now we can, now we have a finite set of directions to test for, right? So of course this is not the only step. At each step we have to find the extremal vertices in the direction d and direction minus d as well. So what do we have to do for this? For this, we can first think of a brute force algorithm. Let's say, for example, you have a certain polygon, and for this polygon we have a certain set of edges, k. And then for each edge, for each direction, we can compute the extremal vertices along d and minus d directions. So if we select, for example, as our direction vector the vector n1, essentially we don't have to compute the extreme vertices for this one, for this edge, because we already know, since we have selected this edge, the extremal vertices for this direction are v1 and v2. All we have to do is to search for the negative, for a direction that is in opposite direction of n1, that is minus d. So we have to search for direction along minus n1. And if we do that, we'll find out that it is this one. So once we find this one, we can compute these two distances and then take the one which is longer, and it looks like this one here. And then do this for all of the edges, one by one, right? And then look which one is which length is the greatest. As you can see, at each step we are taking and we are computing the extremal vertex, and then we also compute two distances. So this is an order of n operation for each edge. So since we have m edges, this is an nn, and hence order of n square algorithm. Remember that this is a brute force algorithm. So what does this mean? Since m equals n, we have n vertices, and hence we will have n the number of edges will be the same as the number of vertices, and this is an order of n square algorithm. So what do we have to do now? Now we will look for better algorithm, and here comes the important step. Now, in the brute force algorithm, we have been searching for all of the possible directions, right? For the extreme vertices of for all the directions. Now, a good question to ask is, could we, for example, let's say, for example, we have run one step of this algorithm for the following special polygon P. I'm deliberately choosing this kind of a polygon because I want a certain normal map to look good and understandable. So that's why I'm doing this. Normally, of course, this algorithm will work on a convex polygon. These are all its normal vectors here. This is v1, v2, v3, v4. Here I have e1, e2, e3. Sorry, e1, e4, e2, e3. Yes. Now, let's say, for example, we have run one step of the brute force algorithm. And say that we have started with the direction corresponding to the normal vector of edge 1. We can immediately say the extreme vertices on this direction are v1 and v2, and in the negative d1 direction, the extreme vertex is v4. And we have also computed the direction, the distance between two vertices, and then we have now a global variable that keeps track of the length of the current maximum and the corresponding pair of vertices on the convex hull. Now, the important question to ask is, we have such an information. Now, is there some kind of how can we make use of this information, local of this current information, to get to the next iteration of the, say, for example, of the next iteration of the brute force algorithm? In the brute force algorithm, we are considering each edge separately. So the order in which we selected the faces doesn't matter. We can select any edge and then search for the extreme vertex of that edge's negative direction, negative or normal direction vector, and then we'll do it. But here in this case, we want to be smarter. We want to find some kind of a connection between the information we have currently, the current iteration, and then we want to select the next direction vector to be the one that will result in a step that will enable us to find the next external vertex in constant amount of time, or a sublinear amount of time. It can be order of 1, order of log n. If it turns out to be an order of n operation, just like in the brute force algorithm, then we won't be able to make it better than the brute force algorithm. Okay, but if we can do it in sublinear time, then it will be a better algorithm. And it turns out that we can do this. So here is the important point, by the way. So in this algorithm, it is important to realize that we are essentially looking for a direction. We are essentially looking at direction as not points. That is the main idea behind the algorithm, okay? So it is not the points, not the edges themselves, but the directions along which we try to search the extreme vertices. That is the main idea behind this algorithm, okay? So let's say, for example, we have started with n1, and let's make this a little bit bigger. Okay, something like this. This is v1, v2, v3, V4, N4, N1, etc. Right? We have started with this one. We have specified that we have found out that this is the extremal direction, extremal vertex along direction minus N1, right? Now, we can think of this as follows. Assume that we have a caliper. So this is where the name of this algorithm comes from, right? Something like this. It has two parallel arms. And we put this caliper such that its arms, these are called caliper's arms, are aligned with one edge of the polygon at each iteration. This makes actually sense because consider the upper arm of the caliper, right? Upper arm, let's consider that upper arm is this one here, right? And the lower arm is this one. And the upper arm is touching the edge E1. And we know that the extreme vertices along the direction of the normal of the edge, the upper arm of the caliper touches are V1 and V2. And the lower arm, this configuration, the lower arm, which is this one, this line here, which is represented by this dotted line, touches the vertex V4. Okay, this one here. So what can we do now? How should we select the next direction? Should we select N2, N3, N4? Well, if we go counterclockwise direction, N2 looks like the next direction, right? But we have to remember that we are not always looking in the N2 direction. The upper arm for the upper arm, the next direction might look like the N2 direction, but for the lower arm, N4 is closer. Why is that? Because remember we had this normal map, direction, space, or normal space. Here's N1. It's not to scale, it's not, I really don't like this, so I want to draw this once more. So let's draw a proper one. This is N1, this is N2. Please observe that touching this polygon with the caliper arms, such that one of the caliper arms is aligned with one of the edges of the polygon, means that the caliper arms essentially are performing, and then you put the caliper in cellular configuration, and then you tighten it. Here's some kind of a knob which you adjust such that this caliper holds this polygon tightly. At this point, you can then tell the distance, the diameter of this polygon along this direction, along the line with the direction vector N1 is that much, okay? Now this caliper, what this caliper is essentially doing, it is trying to find out the extremal vertices along both N1 and minus N1. So if we want to find out what the next direction is, then we have to consider its opposite side vectors as well. So what this caliper does is it simultaneously, if you take a direction D, orient its arms such that its two arm surfaces are perpendicular to a direction vector. In our example, D1 equals N1. Then it will perform a search. This corresponds to a search along two directions, namely D1 and minus D1, or minus D and minus D. In our case, N1 and minus N1. So we have to carry these minus signed direction vectors into our diagram as well. This is minus 2, this is minus N1, this is N3, and this is minus N3, okay? So if you rotate, so at this point our caliper is rotated, our caliper's configuration is like that. And if we rotate the caliper in counterclockwise direction, the caliper's upper arm will hit minus N4, and at the same time, its lower arm will hit N4. And it is that arm which hits the positive sign, positively directed vector, which will align itself with the corresponding edge. For example, here in this diagram, we can see that caliper hits N4, and this is the edge, E4, which aligns itself with the lower part of the caliper, and the upper part will be pointing an extreme vertex. Here we have two vertices for direction N4. We have V1 and V4 as extremal vertices, and then along direction minus N4 we have V2. And by the way, this is the logic behind, if we consider this to be the angle theta, well, what is this angle? How should we call it? I don't know. Should we call it 1 at 4 maybe, right? Because we have selected the caliper to be aligned with N1, and then we're at vertex theta 4, etc. And this somehow corresponds to this angle. Okay, let's drop this here. This is the angle between minus N4 and N1. If you rotate the caliper by this angle, and this corresponds to that angle as well, because we have Z angle here, right? Here, this is theta 2. This is theta, and yeah, this is theta 2. So, this is theta 2. Okay. And now we see that by selecting the next direction vector starting from ny, by selecting the next direction vector to be minus N4 for the upper arm, by the way. For the lower arm, it was minus N1 and then later N4. For the upper arm, the first direction vector was N1 and the second one is minus N4. So you can start, you can keep track of any of the arms, by the way. You can see that the extremal vertex along the N4 direction is, we have hit the lower arm hits the edge, lower edge, and fourth edge, and the upper arm hits vertex V2. And then you can then connect these two. And if we do select our next direction vector to be N2, then we immediately see that the upper arm aligns itself with the edge 2, and the lower arm aligns itself with minus N2. Now you can see some kind of a pattern. Each time the arm that aligns itself with the edge is the one that is drawn at the tip of the normal vector itself of the corresponding edge. So here, and the other arm then touches the minus sign, the opposite direction vector, the opposite of N2. Okay, you can see it here. This is the upper arm, and this here is the lower arm. And as you can see, each time we change directions, we change the extremal vertices by 1. So we have here, each time a new vertex is added or removed. The first for N1 we had V1 and V2. For minus N4 we had V2 here, and then V2 we add V3 here, and we had here in the first iteration V4, and then we had V4, V1, and we removed V4 for the last iteration for selecting N2, and then we chose V2. So here you can see that we are taking a constant amount of computation to select the next one. So if we somehow sort our directions vector by angle, considering all of them, we take all of the vectors and then their opposite signed direction vectors as well. And if we sort these, if it's, for example, and sorted direction vector looks like this, now you can see that it is enough to consider the first 4 directions, the first 4 normal vectors. First 4 directions to be exact, for the upper arm. For the lower arm, we have to start we are starting from minus. If we start from if we align our upper arm the first edge, then the lower edge will be visiting these directions in the same order. This is upper arm and this is lower arm. Okay. So we do this for all of the possible directions, and we have constant amount of work to do at each iteration by selecting our direction vectors using the local for using the connectivity information and direction vector information wisely and smartly. We get an order of an algorithm overall. So why was this? Why did we go through all of this trouble to explain this? It was very important to make use of the information available to us from earlier lectures. And also, the important fact was we are not essentially doing a search in a mixed space in both, you should not think in terms of the polygon and its edges and its normal vectors, etc., or angles. What we are essentially doing is we are searching in the direction space. It is in the normal space. That was the most important insight. Okay, and if we apply this to 3D, it's a little bit more complicated. I haven't thought about this too much. I have some idea as how to do it, but I think this will give a good idea how to generalize this to the 3D. So important insight is, first, extremal vertices correspond in any given direction correspond to vertices of the polygon. The second direction was that the farthest points are always on the extremal vertices, right? And then we combine these two to find out that we have to search for a direction such that if we find the extremal vertices along the directions d and minus d, then we can we can select d such that the distance between those two extreme vertices will be maximal. So this was the important insight. I hope I've been able to explain everything clearly. It was a little bit maybe too verbose, but I hope this was helpful. And if I can find time to shoot a 3D version of this, I'll let you know. Thank you. Take care.